Welcome. In this video, we tackle section 3.9, derivatives of exponential and logarithmic functions. We look at the natural log, exponential functions, logarithmic functions, and logarithmic differentiation. All of these can be made possible with implicit differentiation. This is why we studied implicit differentiation before this. We will use this to expand our base of what kinds of functions we can take derivatives of. All right, let's go. The natural log. What is the derivative of the natural log function? So here's the answer. I'll just give it to you right away. The derivative of the natural log is 1 over x, provided that x is greater than 0. So real quick, let's just see why this x greater than 0 is required. The natural log looks something like that. It's not defined at 0, and it's not defined for negative numbers. 1 over x looks like this, very roughly, very rough graphs. So it's defined for both negative and positive values. But if I'm taking the derivative of the natural log, then only the positive values are of concern. So I only want the positive values for 1 over x. And so whenever I'm working with natural log of x, I'm really only concerned with values of x that are strictly greater than 0. Using this rule, suppose I plugged in something different from x, like an actual function. Suppose I had d dx natural log of u. What would the answer be? Now this is implicit differentiation. I'd end up with 1 over u times du dx. And I won't keep on writing greater than 0. It'll just be assumed from now on. This more general form is what we'll use for a lot of our computations. In fact, the 3 that are on this screen. All right, let's try the 3. So this first one, what's the derivative of the natural log of x to the 4 plus x? So I take 1 over x to the 4 plus x times the derivative of that denominator. So times 4x cubed plus 1. And I can write this as 4x cubed plus 1 all over x to the 4 plus x. In fact, let's go back up to our general expression, and that derivative du dx, I could put that on top. In fact, let me do that right now. Du dx divided by u. This is really the nice general form that we often see. All right, second problem. The natural log of sine of x. Well, what does my rule tell me? I put the argument on the bottom, so I have a fraction, sine x goes on the bottom, and the derivative, du dx, should go on top, cosine x. Well, that's kind of weird, right? Cosine x divided by sine x, otherwise better known as cotangent x. And that's kind of crazy, right? Who would have thought? Who would have thought that the derivative of the natural log of sine of x would be something so nice as the cotangent of x? Third problem, the tangent of natural log. Now, in this case, the natural log is on the inside. The derivative of tangent is secant squared. I take the derivative of the outside, but the inside remains unchanged. Then I multiply times the derivative of the inside. There we go. Why does this rule work? Let's actually prove this. And the first thing we do is let y equal the natural log of x. My goal is to figure out dy dx. So y equals the natural log of x. Now, if I take both sides as the power of e, then that tells me that e to the y equals x, right? E to the y equals e to the natural log of x, and then this guy is really just x. And now I can use implicit differentiation to compute that. Differentiate both sides with respect to x, and we get e to the y dy dx equals 1. Do you see how that works? And now solve for dy dx, and I find that dy dx equals 1 over e to the y, which is really just 1 over x. Remember, e to the y is x. Exponential functions. Now, these are just general exponential functions, things like 2 to the x or 5 to the x, not just e to the x. And we can even do, more generally, things like 2 to the sine x or 5 to the square root of x. Okay, let's see how this works. The derivative of b to the x is the natural log of b times b to the x. How would it work if something more general was put in place of x? D dx of b to the u is the natural log of b times b to the u du dx. So very often this is the form we use. All right, let's see what happens. In the first case, I'm taking the derivative of 2 to the x. Well, that really is just our basic form. So the answer is the natural log of 2 times 2 to the x. The second problem is similar. What's the derivative of 1.05 to the x? It's just a number raised to the x power. That derivative is the natural log of 1.05 times 1.05 raised to the x. In the third problem, instead of just x as our exponent, we get a whole new function. It's like the u up above. So this derivative is the natural log of 2 times 2, and it stays sine of x, but then I need to multiply times the derivative of sine x, which is cosine x. Lastly, I have the derivative of 1.05 raised to the x divided by 4. So the derivative is the natural log of 1.05. You know, in all these problems, I always start with the natural log of the base, natural log of 1.05, times 1.05 raised to the original exponent, so x over 4. But now I need to multiply times the derivative of x over 4. What's the derivative of x over 4? Do you know? It is 1/4. There we go. So that's our rule for the general exponential function. Let's see why it works. What's the proof? Here we go. So let y equal b to the x. My goal is to figure out dy dx. So if y equals b to the x, take the natural log of both sides. The natural log of y is the natural log of b to the x, and this is a great property of logarithms. In general, log of, with any base, the log of m to the n equals n times log base b of m. So that exponent comes out in front. And that's exactly what's happening here. The natural log of b to the x, that x comes out front, that's the same as x times the natural log of b. And now we differentiate both sides with respect to x. So both sides being the natural log of y and x natural log of b. So the derivative of the natural log of y is 1 over y dy dx. And on the right, the derivative of x times natural log of b. Oh, well, look at this. Natural log of b, that's just a constant, like a 5 or a 10. And if I have the derivative of 5x, the answer is just 5. So the derivative of x times ln b is simply ln b. And now let's solve for dy dx. So I just need to multiply both sides by y. dy dx equals the natural log of b times y. And I'm almost there. I almost have what's in the blue box. What's remaining is this y. Well, what is y really? Y is really b to the x. So here we go. Dy dx is the natural log of b times b to the x. There we go. Moving on, general logarithmic functions. The derivative with respect to x of log base b of x is this, 1 over the natural log of b times x. For example, the derivative of log base 2 of x, now 2 is my base, not just the natural log base 2 of x is 1 over the natural log of 2 times x. What if I put something more complicated than simply x? Well, this is where I need to use the chain rule. And so I get 1 over the natural log of 2. I continue to write the sine of x, but then I need to multiply times the derivative of sine x, and I get cosine x. All right, I'll not prove this one. We actually don't use this all that often, and the proof is pretty similar to the ones we've seen before. Moving on, this brings us to logarithmic differentiation. I think that logarithmic differentiation is actually pretty cool. It's a method to compute functions of the form f of x raised to the g of x. For example, we know how to differentiate a function like x to the 5. That's 5x to the 4. And I know how to differentiate a function like 5 to the x. We just learned that. That's the natural log of 5 times 5 to the x. But what if I had a function like 5x raised to the square root of x? That's just weird. I have an x in my base, and I have an x in the exponent. How in the world am I supposed to figure that out? Well, that's exactly what logarithmic differentiation helps us figure out. Let's see. Here's an example. Let's compute the derivative of sine of x raised to the square root of x. Here's the process. First of all, set y equal to the thing you want to differentiate. Next, take the natural log of both sides. On the left, the natural log of y is the natural log of y. On the right, I did a little bit of a trick there. Next step, differentiate. On the left, the derivative of the natural log of y is 1 over y times dy dx. On the right, I have a product rule. I take the derivative of the first, 1 over 2 root x, times the second, natural log of sine x stays there, plus the first times the derivative of the second. And the derivative of ln sine x is 1 over sine x times cosine x. Now my goal is to get dy dx by itself. So to do that, I multiply both sides by y. And so the y appears here, multiplied times everything else that was on the right side. One simplification I did was to turn 1 over sine x cosine x into cotangent x. Then, let's substitute out what the y really represents. After all, y is really the sine of x raised to the square root of x. And so this dy dx, I pull that y out front, and this becomes the derivative of sine x to the square root of x. And the y in front of the brackets, that's just my sine x to the square root of x. And look at that. That is exactly what I sought from the beginning. It's messy, it's beautiful, but there it is. It is true. That is our answer. I wanted to compute the derivative with respect to x of sine x raised to the square root of x, and this is our answer. The sine of x raised to the square root of x times the quantity 1 over twice the square root of x times the natural log of sine x plus the square root of x times cotangent of x. There we go. In this lesson, we've really expanded our set of functions that we can take derivatives of. The natural log function, general exponential functions, general logarithmic functions, and even functions of the form a function raised to another function. And so we can really see this is all because of implicit differentiation. It's the implicit differentiation that allows us to figure out these new rules. All right, and this is a good place to stop.